And I don't mean that it's a good story. I mean it's just a story that's being told to you. A simple harmonic oscillator had to have three principal features. It had to oscillate, meaning it goes back and forth on the same path, had to do it in the same amount of time, and had to be able to be modeled using a sine or a cosine function. Using Hooke's law, we knew the spring mass oscillated, but we were able to show that the parameters of those oscillations generated a differential equation, that one, and that, moreover, a solution to this differential equation could be established by using the cosine function or the sine function. In fact, we found using the derivative that these three functions completely met up and were aligned with this differential equation. That was yesterday. We did more than that too yesterday, not a whole lot more, just enough, because we also did this for a specific system, the spring mass system. So I'll leave up on the board the generic system. But today I want to take some features of that generic system and kind of play with it a bit. And then we're going to take a look at other systems. Ready to begin? The first part of this that I think I need to emphasize is there's information presented in these equations that might not be obvious, that I need you to now see. So let's, for a moment, just kind of focus our attention right here. There were boundary conditions given. Those boundary conditions were that x was at its maximum displacement at time equals 0, and the velocity was 0 at time equals 0. Those are boundary conditions, but those boundary conditions forced us to choose the cosine function over the sine function. So the reason why x is in terms of cosine isn't because there wasn't another solution, but because it met up with our boundary conditions better. We could have chosen sine and added a phase shift, but that's not necessary. It's overly complicated when the cosine function already is at a maximum at time equals 0. These three functions then are developed by taking the derivative of position to get velocity and the derivative of velocity to get acceleration. So that's where we ended up at the end of yesterday, correct? At time 0, this function is at x naught. How long do we have to wait until we are back at x naught? What does the inside of this function have to advance to? 2 pi. So the period is defined as the time it takes for one oscillation. So if I set the inside of any of those functions equal to 2 pi, notice I changed from a lowercase t to a capital T because I'm talking about the time it takes for an oscillation. And as you just said, an oscillation is how long it takes to advance by 2 pi. Then that would suggest that the period of any oscillator would be 2 pi divided by that constant, c. I want you to think about this for a minute. 2 pi is a unitless quantity. The only way this actually works is if c is in units of radians per second. Thus the 2 pi is there, and inverting that gives us seconds. So this must be in radians per second as well. It has to be. Now, if you don't believe me, let's prove it. K is the spring constant. It's in newtons per meter. M is in kilograms, because it's the mass. A newton is a kilogram meter per second squared, all divided by meters times kilograms. I think the kilograms and meters all cancel out there, don't you? So this has to be 1 over seconds squared, which gives us radians per second. No matter what, whatever we derive, it will have to end up having units of radians per second as our constant. It will have to. That's why the term for C is often called the angular frequency and is given the same symbol as we use for angular velocity. Angular velocity is in radians per second. Angular frequency is in radians per second. So often that expression for C is given the symbol omega. It's even on your equation sheet this way some years. It stands for angular frequency. So that C, all of that stuff is the angular frequency. How do you convert something from radians to oscillations? What if I said the word rotations and not oscillations? How would you convert from radians to rotations? You would divide by 2 pi, that's right. So oscillation is a rotation. It takes you back to the starting point. So if I take oscillations and divide by 2 pi, so if I take radians and divide by 2 pi, I'll get oscillations. It's funny because the inverse of period is frequency. Frequency would be C divided by 2 pi. Right? Doesn't that meet up with our expectation? In both cases, the period here is going to be 2 pi times the root of m over k, where this is going to be 1 over 2 pi times the root of k over m. This is for a spring mass system. Whatever C is, has to work out there. Now, I want to stop. So our little thing in the classroom, the mass is 0.2 kilograms and K was 18 newtons per meter. So find me the period, find me the frequency. You only really have to find one. So 2 pi times the root of m over k. Why are you looking at me like I didn't tell you what to do? I told you what to do. I want both of them though, so hurry it up. That's why I said have a calculator out. You're participating. Barely. Don't make me start calling you out. Give it to me right now. What is it? The period is 0.66 seconds. That one's hard. Let's do frequency instead. What's the inverse? 1.5 hertz. Oscillations per second. With that, and like I said, we got nice and close. You now have a way of finding the period of oscillation. If you can produce this relationship, you can immediately figure out what your predicted period of oscillation would be. I know you don't understand how to do this yet, but that's what we are doing. But there's more that I want you to know. I said I want you to be able to do period and frequency, and what else?
The max velocity.
Max velocity of the system. Let's look. We have an expression for velocity, don't we? This expression oscillates between two values, a positive number and a negative number. And that's because we have sine here. Sine's going to be, what's the biggest value sine can be? 1. And the smallest value can be? -1. Yes, it can also be 0, but -1 is still smaller than 0, correct? Based on the way numbers work. But if all I care about is speed, then I think you would all agree 1 is the biggest sine can be here, correct? That suggests that V max must be equal to C times X naught. Must be. Where V max for a spring mass oscillator must be the square root of K over M times X naught. This must be as fast as the system can go. Let's prove it. Right? We can do this another way. So I want to prove something to you. This might be tough. We'll see. To prove it to you, I need to get I need something that you can look at, something that will help you see something. expressions for position and velocity. We should be able to test to see if that's true. I know you don't know where I'm going with this, so allow me. Slide that over to the side, and let's take a look at something that we do know. The total energy of the system has to be the combination of the kinetic energy and the potential energy. That's what we just said a moment ago, right? But we have an expression for our potential energy. We have an expression for our position and an expression for our velocity. So how about we put those in? 1/2 mv, which is negative c x naught sine ct, quantity squared, plus 1/2 k x, which is x naught cosine ct, quantity squared. This has to be the total energy, but now this is the total energy as a function of time. And we know the energy is going back and forth between these two things. Let's go ahead and expand this. I get 1/2 mc squared x naught squared sine squared ct plus 1/2 k x naught cosine squared ct. X squared 2, thank you. That doesn't tell me very much yet, except C equals the square root of x over m for a spring mass oscillator upon which this is based. Right? Is that true or not? You guys see what I'm doing? I'm going to sub in for the C. And I'll get 1/2 mc squared, which is just k over m, x naught squared sine squared ct plus 1/2 k x naught squared cosine squared ct. Do you see that the m's cancel? Right here. Do you notice that all I have left is 1/2 k x naught squared? And do you notice I have the same term here? So I could just factor those out. And I'd have sine squared ct plus cosine squared ct. Tell me what you know about sine squared and cosine squared when you add them together. Is that evidence enough that the total energy, regardless of what point in time we look at it, is always going to be equal to the energy that the system started with? Right? Proved it. Our functions have to work this way. These systems conserve energy. This isn't an accident. It's a consequence. I think this will help. You have access to this, right? This is just a little bit of a template. Let's start by recognizing that the top one is equilibrium, so I've marked equilibrium. Is that good for you guys? Because I really want to focus on this quarter of a oscillation. Can we agree, or try to, that this is x naught, because at this moment v equals 0? Right, this is where we released it. So it is instantaneously at rest at its maximum displacement. How much kinetic energy is there? Kinetic energy is 1/2 mv squared. What is v? So how much kinetic energy do I have? That's a lot harder than I really thought it would be. If the energy is not in kinetic, where must it be? So the maximum amount of elastic potential energy must be 1/2 k x naught squared. After it has moved for a few minutes, it has a velocity in this direction and is no longer at its maximum displacement, is experiencing a force and is accelerating to the left. At this instant, we have both kinetic energy and potential energy. 1/2 mv squared plus 1/2 kx squared. But do you realize that that has to be equal to 1/2 kx naught squared? That the total energy can't change? Seems a little weird though, doesn't it? Because we have, over here, the position is 0. How much potential energy is there here? 0, right? So all the energy is in the form of what kind of energy? Kinetic. So 1/2 mv max squared is what's happening right now because all the energy is kinetic. This is the maximum amount of kinetic energy, right? Doesn't this have to equal the amount of potential energy we started with? So 1/2 kx naught squared equals 1/2 mv max squared. We can solve this for v max, can't we? Cancel out the 1/2s. Solve for v max. And I'm noticing that we get the square root of k over m times x naught. Are you noticing that too? It has to be this way. That's what we said it would be based on the motion equations. Now we've proven it using energy. I wanted to make sure I established that these have to work this way. But also, they're generic. We should be able to apply it to any system if that system has the same kind of differential equation, the same relationship between acceleration and displacement. Right? That's still what we have on this screen sitting over here. So what we need to do now is part 2. We've established part 1, I hope, that if we have the second order differential equation, and it is equal to minus a constant times position, I'm switching to constant to use the more accepted value of omega and not c, that this will generate a host. Yes, thank you. This will generate a host of equations that describe the motion of the object. You don't have to rewrite them a second time, unless you're trying to help memorize them. And from there, period is 2 pi divided by omega. Frequency is omega divided by 2 pi. And Vmax is equal to omega x naught. These will have to be true. So, I want to see something. What's that? I have x naught. That's supposed to be there. Oh, thanks. Duh. Trying to go fast, I guess. The idea now is to be able to take this and apply it to other systems. Not just any system. We wouldn't apply this to an object rolling down a ramp. It's not oscillating. But we would apply it to systems that oscillate. So that's what I want to do. I want to apply this to systems that oscillate. And the system I want to look at is this system. You're going to need your calculator for something here in a minute, though, so make sure you have it. This is going to be an oscillate. I'll be calling on different tables because we need a piece of information before we get started here. And it'd be nice to get it front-loaded rather than at the end. So I want to, if there's a relationship, this is our pendulum. We are picking a single instant in time. In the pendulum, I want to mark a few things like the vertical. Mark the vertical here to indicate that we have a point of reference. The pendulum has been displaced in angle theta. Would you agree that there exists a force that's going to try and displace the pendulum back to equilibrium? Okay. We have a decision about how we analyze this. We can analyze it using forces or analyze it using torques. I have made that decision for you. We're going to use torques. It's easier. But if you want to use forces, that's fine. But you have to use arc length if you're going to use forces because it travels in an arc. So it's easier to use torque. I'm going to give this some parameters. I'm going to say that a pendulum has a length. And it's a simple pendulum. We'll do physical pendulums tomorrow. This is a simple pendulum. So the length is along a massless string, and all of the mass is concentrated at the bottom. I believe there exists a torque based on the fact that there are two forces that act on the pendulum bob: weight and tension. Does the tension apply a torque to the pendulum? It does not, based on the angle, because our torque arm is from the pivot point to the center of mass, and it looks like the tension has an angle of 0 between the torque arm and the force. If I recall, torque is R times F times the sine of the angle between them. I do believe that the weight is causing a torque. The weight is acting downwards. Based on the position of the pendulum, this would be the angle between the torque arm and the weight. So I believe I can write the torque on the pendulum as L times mg times the sine of theta. Can you guys agree with me that theta is into the board, but the torque is out of the board? Right-hand rule, this way, into the board. That's the direction of the displacement. But the torque is trying to cause it to go this way, out of the board. Seems to me the torque is in the opposite direction of the displacement. This is the only torque acting on the system because the only other force is acting at the pivot point. So this has to be equal to I alpha. As I recall, alpha is d omega dt, and omega is d theta dt. Seems to me this could be written as I times the second derivative of theta with respect to t. Can I do that fast? Is that fast enough? Is that okay? Or is that too fast? So I'm just doing that substitution. And that's going to be minus L mg sine theta. Getting close. I have the second derivative of theta with respect to sine of theta. That's not my function. But let's clean this up. Moment of inertia. This is a point mass. I can cancel the m's, can't I? And one of the l's. So cancel the m's, cancel one of the l's. In fact, I'm going to move everything to one side and isolate the derivative. Boy, this would be perfect if it wasn't for the sine theta, wouldn't it? Tell you what. I'm going to make sure that my pendulum is only oscillated at small angles. Does it fit? Is it what we have over here? Sure is, as long as we say that C equals the square root of G over L. Right? C squared equals the constant. Again, omega would be better here. But I didn't want you to get confused with this omega, which represents the angular velocity of the pendulum, not the angular frequency of the system. But this also tells me a bunch of stuff about a pendulum all of a sudden. For example, T must equal 2 pi divided by c, or 2 pi times the square root of L over G. That must be the period of a pendulum. The frequency of a pendulum must be 1 over 2 pi times the square root of G over L. In fact, I could probably generate a whole host of equations right now. I could probably do theta as a function of t, omega as a function of t, and alpha as a function of t. One more thing. I've said to you that for every oscillator, its inertia makes it move slower, and restoring force can make it go faster. Do you see inertia in L here? It's hard to see it. Let me help you. This came from me just putting, if I multiply top and bottom, do you see the semblance of where inertia was, ml squared, and mg being the force? The reason we don't see inertia and force here isn't because it isn't there. It's because mass and gravity tend to cancel out. All right, folks, that's all for today. I want to add something to this discussion. Got to be honest with you, third period did this amazingly well. Sixth period, terrible at it. Terrible. There's only 6 tables here, so we'll only do this 6 times. And I'll fill in the gaps. That's not quite as many as I want. I should do 10 degrees in here, so let's do 10 in there too. I want you to convert all of these from degrees to radians, and then I want you to take the sine of those angles. I ask you if you see what's happening here. Do you notice as the angle gets smaller, the value in radians is very nearly equal to the sine of that angle? This is called the small angle approximation. And we say that theta equals sine theta for small angles. It's for small angles. If the angle gets bigger, the difference between the two gets bigger as well, which means that if you use the small angle approximation, you are saying that theta equals sine theta in limited circumstances. Because I have a pendulum here. I can clearly demonstrate that a pendulum is an oscillatory motion. In fact, I think I can go as far as to say it's a harmonic oscillator. Wouldn't you say that? It appears to move back and forth with the same period of oscillation. So the question is it a simple harmonic oscillator? For that we must study. For that we must apply Newton's laws and see if there is a relationship between the displacement and the acceleration. I can't leave this up because you guys can't be trusted. But we are going to see